it vanished instantly. Not dimmed, not faded over weeks or months in the way that dying stars typically announce their endings. Not exploded in the spectacular violence of a supernova that briefly outshines entire galaxies. Not collapsed into a black hole through the prolonged drama of a stellar death that leaves its mark on the surrounding interstellar medium for thousands of years. Vanished in a time frame shorter than the observational cadence that was monitoring it. Between one observation and the next, there one moment, bright, luminous, a massive star that had been burning for millions of years and then gone. No explosion, no remnant, no trace of what happened. Just absence where a star had been. This is not science fiction. This is an observed phenomenon, documented in peer-reviewed literature, confirmed by independent teams using independent instruments, and it is one of the most genuinely mysterious astrophysical events currently lacking a satisfying explanation. The specific events I'm going to describe involve a small number of massive stars scattered across different galaxies that have simply ceased to exist as luminous objects without producing the expected signatures of stellar death. They're not common, they're not well understood. And they're forcing astronomers to confront the possibility that some of the most massive stars in the universe are dying in a way that our current understanding of stellar physics doesn't fully predict. But here's what makes this story genuinely extraordinary. It's not just about the mystery of vanishing stars. It's about what those vanishing stars might be telling us about one of the most fundamental and least understood processes in astrophysics, the direct formation of black holes from stellar collapse without a visible supernova, and potentially, in the most extreme and speculative interpretations, about something even more exotic. Let me start at the beginning with what we expected to happen when very massive stars die. Stellar death in the standard picture is not quiet. It's extraordinarily violent. When a massive star, say 20 times the mass of the sun, exhausts its nuclear fuel, the iron core collapses in a fraction of a second. This collapse releases about 3 times 10 to the 46 joules of energy, comparable to the total energy output of the sun over its entire 10 billion year lifetime, released in about 1 second. The outer layers of the star are blasted away in a core collapse supernova, an explosion so luminous it briefly outshines entire galaxies. What's left is a neutron star or a black hole embedded in an expanding nebula of processed stellar material. The nebula glows for thousands of years. The neutron star or black hole emits various forms of radiation. The explosion is visible across billions of light years. The death of a massive star is an event that announces itself to the universe. This is the standard picture. This is what the models predict. This is what we've observed many times in nearby galaxies, supernovae that light up and fade over weeks to months, leaving behind remnants that we can study for millennia. But there's a subclass of stellar deaths that the models have long predicted might be different. Stars at the very top of the mass spectrum, stars above about 40 to 60 solar masses in some models, or above certain combinations of mass and core structure, might collapse directly to black holes without producing a visible supernova, or with only a very faint, brief optical transient before the black hole forms and swallows everything. This is called a failed supernova, or a collapsing star, or direct black hole formation. The terminology varies, but the physics is specific. A star massive enough that when its core collapses to a black hole, the black hole forms before the shock wave that drives the supernova explosion can successfully propagate outward. Instead of the explosion winning and blowing the star apart, the black hole wins and swallows the outer layers. The star disappears, or nearly disappears, rather than exploding. Failed supernovae were predicted theoretically for decades before anyone found observational evidence for them. The prediction was uncomfortable in a specific way. If some fraction of massive stars disappear instead of exploding, it affects our entire accounting of stellar death, how many neutron stars and black holes there should be, what the rate of heavy element enrichment is, what fraction of stellar mass is returned to the interstellar medium. Failed supernovae are consequential, and finding them requires a specific observational strategy. You have to watch a large number of massive stars continuously for years, waiting for one of them to disappear. Not explode, disappear. The systematic search for failed supernovae was pioneered by Chris Kokonek at Ohio State University, who in the mid-2000s began advocating for exactly this type of monitoring program. The strategy he proposed was straightforward. Monitor a large number of galaxies with regular imaging, identify all the massive stars in those galaxies, and wait for them to die. If a massive star disappears without producing a supernova, you found a failed supernova. This is easier said than done. It requires long-time baselines, years of observations. It requires consistent imaging of the same fields. It requires careful photometric calibration to reliably detect the disappearance of a single star against the background glow of its host galaxy. And it requires a way to distinguish a genuine stellar disappearance from a star that has merely become obscured by dust, or has entered a phase of extreme dimming, or has been outshone by a nearby variable. The Large Binocular Telescope collaboration, a project using the Large Binocular Telescope in Arizona to monitor nearby galaxies for stellar disappearances, began systematic observations in 2008. They called their survey the Large Binocular Telescope Single Star Survey, or more commonly, the Failed Supernova Survey. By 2015, they had found something. The candidate was in the galaxy NGC 6946, known informally as the Fireworks Galaxy because of its unusually high supernova rate. 9 supernovae have been observed in NGC 6,946 inches the past century. It's one of the most actively star-forming spiral galaxies in our cosmic neighborhood, located about 22 million light-years away. The star designated N6946 BH1 was identified in archival Hubble Space Telescope images as a bright red supergiant. Its luminosity before disappearance corresponded to a stellar mass of roughly 25 solar masses. A massive star nearing the end of its life in a galaxy known for its stellar violence. In 2009, the star briefly brightened a modest optical transient, roughly 1 million times the sun's luminosity, lasting for several months. This brightening was consistent with a failed supernova scenario. When the stellar core collapses and the shock wave fails to explode the star, some material may still be expelled in a relatively weak, brief outburst before the black hole swallows the rest. After the brightening, the star should have disappeared as the black hole consumed the outer layers. And it did. Subsequent monitoring showed that N6946 BH1 had essentially vanished, replaced by a source far too faint to be the original star. Deep Hubble imaging and infrared observations confirmed that the stellar source had disappeared. No supernova had been observed. The star had brightened briefly and then essentially ceased to exist as a luminous object. The team's analysis, published in 2017, argued that this was the first confirmed case of a failed supernova, a massive star collapsing directly to a black hole without a visible explosion. They estimated the mass of the resulting black hole at roughly 6 solar masses, consistent with the amount of matter that would remain after the failed explosion expelled some of the outer layers. The discovery made headlines. Astronomers celebrated. We may have just seen a failed supernova. The press releases said, star disappears, apparently eaten by black hole. But then the story got more complicated. Follow-up observations of the N6946 BH1 field conducted over subsequent years added nuance to the initial interpretation. The site is not completely dark. There's a faint infrared source at the location, consistent with dust heated by either a low luminosity remnant or by the previously expelled material. Some analyses suggested the original star might have undergone a dramatic brightening, followed by extreme dust formation that obscures the stellar photosphere, making it appear to have disappeared without actually dying. The ambiguity reflects a genuine difficulty in interpreting stellar disappearances from a distance of 22 million light-years. A star that truly disappears because it's been swallowed by a black hole looks observationally similar to a star that has surrounded itself with an optically thick dust cocoon. Distinguishing between these requires careful spectral energy distribution modeling across a wide range of wavelengths. The community consensus on N6946 BH1 is that it remains the best candidate for a failed supernova observed to date. But best candidate means strong evidence, not proof. The alternative, extreme dust formation following a non-terminal stellar outburst, cannot be completely ruled out. What's significant is that this ambiguity is not unique to N6946 BH1. There are several other massive star disappearances in the observational record that share similar characteristics: a brief brightening followed by apparent disappearance without a classical supernova signature. Let me tell you about another case that's generated significant discussion. One that's in some ways even more puzzling than N6946 BH1. In 2019, astronomers studying the Kinman Dwarf Galaxy, a small, low metallicity galaxy about 75 million light-years away, noticed something unexpected in their observations. The galaxy had been monitored for years and had contained a prominent luminous blue variable star, or LBV, that had been detectable in spectroscopic observations going back to 2001. Luminous blue variables are among the most massive, most luminous stars known. They're unstable. They undergo dramatic episodes of brightening and dimming, sometimes ejecting large amounts of material in events called giant eruptions. They're expected to evolve into Wolf-Rayet stars and eventually die as core collapse supernovae. They're violent, spectacular objects. The LBV in the Kinman Dwarf Galaxy, designated PHL 293b after its position in older catalogs, had been consistently detectable in spectroscopic observations for about 2 decades. And then, in observations conducted in 2019, it was gone. Not dimmed, not variable, gone. The spectroscopic signatures that had been present in every prior observation, hydrogen emission lines characteristic of the luminous blue variable stellar wind, had completely disappeared. The team that discovered the disappearance, led by Andrew Allen of Trinity College Dublin, published their findings in 2020. They considered several possible explanations. The first was that the star had experienced an extreme eruption, like the giant eruption of Eta Carinae in the 19th century, that had ejected so much material that the optically thick ejecta now obscured the stellar photosphere. In this scenario, the star is still there but hidden behind its own expelled material. The spectroscopic signatures disappeared because the spectrum is now dominated by the cool, slowly moving ejecta rather than the hot stellar photosphere and wind. The second possibility was that the star had undergone some kind of transition into a radically different phase, perhaps a direct collapse to a black hole without a supernova. In this scenario, the star is genuinely gone. The third possibility, and this is where the story gets particularly interesting, is that what astronomers thought was an LBV was actually not a single star, but a system of multiple stars, or a stellar merger product, and the apparent disappearance reflects changes in the system's configuration rather than the death of a single object. Disentangling these possibilities requires continued monitoring, deep imaging, spectroscopic follow-up with large telescopes, and time. The Kinman dwarf case remains unresolved. Now, I want to zoom out from these specific cases and address the broader context. How common are these stellar disappearances? And what do they tell us about stellar physics? The current estimate from the ongoing monitoring programs, combined with theoretical models, is that something like 10 to 30% of massive stellar deaths might be failed in the sense of producing no bright supernova. Not all massive stars produce visible explosions. A significant fraction, perhaps a quarter or more, might simply collapse directly to black holes, appearing to vanish rather than explode. This has consequences. The rate of visible core collapse supernovae, the bright explosions we observe, would then be systematically lower than the total rate of massive star deaths. We'd be missing a fraction of stellar deaths in our observations. This affects the inferred rate of black hole formation, the rate of heavy element release into the interstellar medium, and the overall accounting of stellar mass in the universe. There's actually independent evidence that the core collapse supernova rate might be too low relative to the rate predicted from the star formation rate. The number of core collapse supernovae we observe in nearby galaxies appears to be perhaps 30 to 50% lower than what you'd predict from counting the massive stars available to explode. This supernova rate problem has been discussed in the literature for years. Failed supernovae stars that collapse without visible explosions would naturally explain part of this discrepancy. The connection between the observed stellar disappearances and the supernova rate problem is compelling. These might be different observational signatures of the same underlying phenomenon. Massive stars that collapse directly to black holes without the conventional supernova explosion mechanism succeeding. But here's where the story becomes genuinely strange. And this is the part that I find most scientifically provocative, because some of the reported stellar disappearances don't fit neatly into the failed supernova framework either. Let me tell you about a particularly puzzling class of disappearing stars. Stars that vanish without any prior brightening, without the transient optical emission that you'd expect from even a failed supernova. Stars that simply stop being there. The mechanism for a failed supernova, even a completely failed one, still involves some energy release as the stellar core collapses. The core bounce produces a neutrino burst even in a failed explosion. Some material is likely expelled in a weak shock before the black hole forms and swallows everything. Some gravitational energy is released as the outer layers fall into the forming black hole. All of these processes produce some electromagnetic emission, perhaps brief, perhaps faint, but some. A truly instantaneous disappearance, a star that's there in one observation and gone in the next with nothing in between, is harder to explain even within the failed supernova framework. And yet there appear to be cases in the literature where this is what's observed. Stars, massive, luminous, well documented before their disappearance, that vanish without any detectable transient. The temporal resolution of the monitoring determines how constraining this is. If observations are separated by months, you might simply have missed a brief transient. If observations are separated by days or weeks, the absence of a transient becomes more constraining. Some of the disappearances in the literature are consistent with failed supernovae that produce brief, weak transients below detection thresholds. Others are in tension with even this weak scenario. I want to now introduce something that's more speculative but genuinely scientifically discussed. A possibility that's at the edge of what current physics can address, but that some theorists have considered as a potential explanation for the most rapid, most complete stellar disappearances. It's the possibility that some massive stars collapse directly to black holes on timescales that are genuinely instantaneous by astronomical standards, fractions of a second, without any preceding optical emission. The standard failed supernova involves a two-step process. First, the iron core collapses to a protoneutron star. This collapse takes about half a second and produces a massive neutrino burst. Even in a failed explosion, the neutrino luminosity is extraordinary. Then, over the next seconds to minutes, the protoneutron star accumulates matter and eventually crosses the maximum mass threshold, collapsing to a black hole. During this seconds to minutes window, the star's photosphere is still in place, still emitting light. The collapse is happening in the center. The outer layers don't know about it yet because information can't propagate faster than the sound speed in the stellar interior. And the sound crossing time for a supergiant is hours to days. So the star keeps shining roughly unchanged for hours to days after the core has collapsed. Only then does the photosphere collapse into the forming black hole, extinguishing the light. This gives a potential light curve for a failed supernova. The star shines as normal for perhaps a day, then drops rapidly to darkness as the outer layers fall into the black hole. This timescale is detectable with daily or near-daily monitoring, but what if the collapse is different? What if the star structure is such that the collapse proceeds from core to photosphere faster than the standard model assumes? In stars with very compact structures, very high central densities, very steep density gradients, the infall timescale might be shorter, the photosphere might collapse more rapidly, the star might disappear on timescales of hours rather than days. This is at the edge of current stellar modeling. The specific timescale of the disappearance depends on the detailed internal structure of the collapsing star, which varies with mass, metallicity, evolutionary history, rotation rate, and other factors. Getting this timescale right requires detailed, high-resolution stellar evolution models that incorporate the effects of the collapse on the stellar envelope models that are computationally challenging and that are not yet fully tested against observations. Let me now tell you about the theoretical landscape, about what stellar physics actually says about when and why massive stars might fail to explode. The question of whether a star produces a successful supernova or a failed one is in the current theoretical understanding, determined primarily by the structure of the stellar core at the time of collapse. Specifically, by a quantity called the compactness parameter, defined roughly as the ratio of the core mass to its radius at the time of collapse. High compactness, a dense, compact core tends to produce failed supernovae. In high compactness progenitors, the accretion rate onto the protoneutron star is high, the neutrino-driven shock revival is difficult, and the protoneutron star collapses to a black hole before the shock can escape. Low compactness tends to produce successful explosions. The compactness of the stellar core at collapse depends on the entire prior evolution of the star, 40 to 60 million years of nuclear burning mass loss, mixing, and structural changes leading up to the final collapse. The relationship between initial stellar mass and final core compactness is not monotonic. It's not simply that higher mass stars always have higher compactness. The relationship is complex, and in some models shows a landscape with islands of explodability and failed supernova at specific mass ranges. This theoretical landscape, specific mass ranges where stars fail to explode. separated by mass ranges where stars do explode, make specific predictions about the demographics of stellar deaths. Not all massive stars fail. Not only the most massive stars fail, specific mass windows determined by the details of nuclear burning can produce either exploding or non-exploding stars depending on small differences in progenitor properties. This theoretical complexity makes it difficult to predict for any given observed star whether it will explode or fail, and it makes observational surveys looking for stars that disappear without exploding the most direct way to constrain the fraction of failed stellar deaths. Now let me address something that connects the disappearing star phenomenon to recent advances in observational astronomy that are dramatically improving our ability to monitor stellar populations. The Vera C. Rubin Observatory, which began survey operations recently, is conducting the Legacy Survey of Space and Time, or LSST. This survey will image the entire southern sky every few nights for 10 years in 6 optical bands with extraordinary depth and consistency. Every night it observes will be compared to previous observations of the same fields, and any source that appears or disappears will be flagged in real time. This is exactly the observational strategy needed to find and characterize stellar disappearances. Instead of monitoring specific nearby galaxies with specific telescopes on a specific schedule, LSST will be monitoring all galaxies in the southern hemisphere. Thousands of galaxies containing millions of massive stars every few nights. Any star that disappears will be detected within days of its disappearance. The sample of monitored massive stars will be orders of magnitude larger than the current surveys. The detection efficiency will be dramatically higher, and the temporal resolution a few days between observations rather than weeks to months will constrain the timescale of any disappearance much more tightly. Over 10 years of LSST operation, the expectation is that dozens to hundreds of candidate failed supernovae will be detected if the theoretical predictions about the fraction of failing massive stars are correct. If the observed rate is much higher or much lower than predicted, it will tell us something fundamental about stellar evolution and the stellar death mechanism. And if some of the detected disappearances are genuinely instantaneous, if stars vanish between one LSST epoch and the next, with no detectable transient in between, it will be extraordinary. It will mean that some stellar deaths are producing no detectable electromagnetic signature at all, which would be very hard to explain and would demand new physics. Let me now tell you about something that's more theoretical, but that I think is important for framing the full scope of what we might be observing. A connection between stellar disappearances and gravitational wave astronomy. When a massive star collapses to a black hole, whether through a successful supernova or a failed one, the collapse generates gravitational waves. The amplitude and frequency of the gravitational waves depend on the asymmetry of the collapse. A perfectly symmetric collapse produces no gravitational waves, while a highly asymmetric collapse produces a strong signal. Core collapse supernovae are expected to produce gravitational wave signals detectable by LIGO and Virgo out to roughly our own galaxy, the Milky Way, and perhaps to the nearest galaxies like the Magellanic Clouds and Andromeda. At greater distances, the signal is too weak for current detectors. Failed supernovae might produce gravitational wave signals that are different from successful ones. If the collapse proceeds more rapidly and more symmetrically, if the shock fails early and the proto-neutron star accretes its way to a black hole more efficiently, the gravitational wave emission might be briefer, potentially lower amplitude than in successful explosions. For the specific observed stellar disappearances we've discussed at 22 million light years for N6 946 BH1 and 75 million light years for the Kinman dwarf LBV, the gravitational wave signal would be far too weak for current detectors. We're not going to detect gravitational waves from these events with LIGO, But next generation gravitational wave detectors, the Einstein telescope in Europe and Cosmic Explorer in the United States, will be perhaps 100 times more sensitive than current LIGO. They'll be able to detect gravitational waves from core collapse events, supernovae, and failed supernovae out to distances of tens to hundreds of megaparsecs. The same distance scales where LSST will be detecting stellar disappearances, the prospect of simultaneously detecting a stellar disappearance in LSST's optical survey and a gravitational wave signal from the same event, with the gravitational wave signal potentially distinguishing between a complete failed supernova and a successful one, is one of the most exciting prospects in multi-messenger astronomy for the coming decade. A star disappears in an LSST image. LIGO's successor detects gravitational waves from the same location. The gravitational wave signal tells you about the internal dynamics of the collapse, whether it was asymmetric, how long the protoneutron star survived before collapsing to a black hole, what the final black hole mass was. The combination of optical disappearance and gravitational wave signature would provide the most complete picture of failed stellar death ever obtained. Now, I want to step back from the specific observational phenomena and address the deeper question. What are the fundamental physics reasons that some massive stars might collapse without producing a visible supernova? The key physics is in the neutrino-driven shock revival mechanism, the process by which the shock wave generated by the core bounce is revived by energy deposition from the neutrino flux and drives the supernova explosion. Here's the basic picture. When the iron core collapses to a protoneutron star, a shock wave forms at the surface of the protoneutron star, the core bounce. This shock propagates outward through the infalling stellar material. But as it propagates, it loses energy, both from photodisintegration of heavy nuclei in the infalling material, which consumes energy, and from neutrino losses. The shock stalls. It stops propagating outward. For a supernova to succeed, this stalled shock must be revived, must receive enough energy to overcome the infalling material and propagate to the stellar surface. The energy source for shock revival is the neutrino flux from the cooling protoneutron star. Neutrinos carry away more than 99% of the collapse energy, but a small fraction, about 1%, is deposited in the stalled shock region through neutrino absorption. If this deposition is sufficient to overcome the ram pressure of the infalling material, the shock revives and the star explodes. If not, if the neutrino energy deposition is insufficient, the shock remains stalled. The accretion onto the protoneutron star continues. The protoneutron star mass increases. At some point, the protoneutron star exceeds the maximum mass that neutron degeneracy pressure can support, the Tolman-Oppenheimer-Volkoff mass, which for nuclear equation of state models is roughly 2 to 3 solar masses, and it collapses to a black hole. The black hole then rapidly accretes the remaining stellar material. The star disappears. What determines whether the neutrino energy deposition is sufficient? The neutrino luminosity, the neutrino energy spectrum, the density and composition of the material in the gain region above the protoneutron star, and the turbulence in that region, which can enhance or reduce neutrino absorption efficiency depending on the flow pattern. These factors all depend on the progenitor structure. For some progenitor structures, specifically the high compactness stars I described earlier, the infalling ram pressure is too high. The shock cannot be revived despite the neutrino heating, and the collapse fails. For other structures, the shock revives successfully. The theoretical threshold between exploding and non-exploding stars is not sharp. It depends on the multidimensional nature of the collapse, the three-dimensional turbulence in the gain region, the convective motions inside the protoneutron star, the asymmetries in the neutrino emission. State-of-the-art three-dimensional supernova simulations are only now becoming computationally feasible, and they're revealing a complex picture in which small differences in initial conditions can produce either explosions or failures. Let me close this first part with something that captures why I find the disappearing star phenomenon so scientifically compelling. There are very few phenomena in astrophysics where you watch something that was there and then it isn't. Stars are ancient, they're stable, they're the most enduring structures in the observable universe, burning for millions to billions of years, their light reaching us across cosmic distances. The idea of a star simply ceasing to exist, not exploding, not fading, not transforming into something else that we can detect, but genuinely vanishing challenges something fundamental about how we think about stellar stability and stellar death. And yet the physics says it should happen. The theoretical prediction of failed supernovae made decades ago, refined by increasingly sophisticated simulations, and now apparently confirmed by observation, is a legitimate physical process. Stars above certain masses, with certain internal structures, really should collapse directly to black holes without visible explosions. The universe should contain a population of missing stellar deaths, massive stars that ended their lives silently rather than spectacularly. The observational evidence is accumulating. N6946, BH1 remains the strongest candidate. The Kinman dwarf LBV remains unexplained. And there are other cases in the literature, less well studied, more ambiguous, but consistent with the pattern. We are, right now, building the observational infrastructure that will answer this question definitively. LSST will monitor millions of massive stars. Next-generation gravitational wave detectors will listen for the acoustic signature of stellar collapse. Webb will characterize the infrared properties of disappearing star candidates with unprecedented precision. Within this decade, we'll know how common are stellar disappearances. What fraction of massive stars vanish rather than explode? What does the temporal profile of the disappearance look like in high-cadence monitoring? And possibly, if some of the disappearances are more abrupt, more complete, more instantaneous than even the failed supernova model predicts, we'll discover that some stars are dying in a way that current physics doesn't fully explain. It vanished instantly. That sentence applied to a massive star, documented by modern instruments, confirmed by independent teams, is the beginning of one of the most interesting open problems in stellar astrophysics. And the solution, when it comes, will tell us something profound about the endpoint of stellar evolution, the formation of black holes, and the ways the universe can end the life of a star without announcing it to the cosmos. In part 2, I want to go deeper into the specific physics of direct black hole formation, into what the observations tell us about the demographics of stellar death, and into the most exotic possibilities, the scenarios at the edge of our theoretical framework that some of the more puzzling disappearances might be hinting at. So we'd arrived at this place where stellar disappearances, massive stars that vanish without producing visible supernovae, are a real documented phenomenon that's challenging our models of stellar death. The failed supernova mechanism provides a physically motivated explanation for most of them, but some of the disappearances are more abrupt, more complete, more puzzling than even the failed supernova framework comfortably accommodates. Now I want to go deeper into the specific physics of what happens inside a collapsing star in the seconds to minutes before it becomes a black hole, into what the demographics of stellar death tell us about which stars explode and which ones don't, and into the more exotic possibilities that some theorists have considered, the scenarios that go beyond the standard failed supernova picture and into territory that's genuinely at the frontier of our understanding. But I want to start with something concrete, with the physics of the moment of disappearance itself, the specific sequence of events happening in real time. As a massive star crosses the threshold from existence to non-existence. Let me take you inside the collapse, not metaphorically, physically, into the specific physical processes that unfold in the core of a massive star in the last second of its stellar life. The iron core has been building for years. Not the star's full lifetime. Most of a massive star's life is spent burning hydrogen, then helium, then carbon, neon, oxygen, and finally silicon. Each burning phase is faster than the last. The silicon burning phase, which produces iron and nickel, lasts only days. And then the iron core, which has been growing as silicon burns, reaches the Chandrasekhar mass. At the Chandrasekhar mass, electron degeneracy pressure, the quantum mechanical resistance of electrons to being compressed into the same state, can no longer support the core against gravity. The core begins to collapse. The collapse is extraordinarily fast. The freefall timescale for the inner core, about 0.6 solar masses of material, is roughly a quarter of a second. In that quarter second, the inner core goes from a density comparable to an atomic nucleus, about 10 to the 14th grams per cubic centimeter, to densities several times higher. The compression is so extreme that electrons and protons combine into neutrons and neutrinos. The neutrinos produced at a rate of roughly 10 to the 58 particles per second at peak stream outward, carrying away energy at nuclear density. The strong nuclear force, which is repulsive at very short distances, suddenly provides a new source of pressure. The inner core stiffens. It bounces. This is the core bounce, the moment when the collapsing inner core abruptly halts its infall and rebounds outward, launching a shock wave into the still infalling outer core. The shock wave propagates outward. For the first few milliseconds, it's strong and fast moving. Then it encounters the infalling outer iron core, which it must photodisintegrate, break iron nuclei apart into protons and neutrons, and that photodisintegration consumes energy. The shock slows, loses energy. After about 150 milliseconds, it stalls, it stops propagating outward, and becomes a standing accretion shock, hovering at a radius of roughly 100 to 200 kilometers above the protoneutron star. This is the crisis point. The stalled shock is the moment of decision. Will it be revived or will it fail? In a successful supernova, what happens next is this. The intense neutrino luminosity from the cooling protoneutron star, 10 to the 53 watts, an almost incomprehensible power output, heats the material just below the stalled shock. This heating expands the gain region, reduces the ram pressure on the shock, and generates convection hot material rising, cooler material sinking, that efficiently mixes the neutrino energy into the shock. After a few hundred milliseconds of this neutrino-driven convection, the shock revives and begins to propagate outward again. In a failed supernova, the neutrino heating is insufficient. The ram pressure of infalling material is too high. The gain region is too small. The convection is suppressed by the geometry of the accretion flow. The shock remains stalled. The stalled shock defines what follows. Material continues to fall through the stalled shock and onto the protoneutron star. The protoneutron star mass grows. As it grows, two things happen simultaneously. Its gravitational field strengthens, making shock revival harder, and it approaches the maximum mass for a neutron star. The maximum mass of a neutron star, the Tolman-Oppenheimer-Volkoff limit, depends on the nuclear equation of state, which is itself uncertain. Current observations, particularly the measurement of neutron star masses up to about 2.1 solar masses, constrain the equation of state, and the maximum mass is probably between about 2.1 and 2.5 solar masses. When the protoneutron star reaches this mass, it can no longer support itself against gravity. It collapses to a black hole in a timescale of microseconds. When the protoneutron star collapses to a black hole, something dramatic happens to the neutrino emission. The protoneutron star had been emitting neutrinos continuously. Its neutrino luminosity was providing the energy, attempting to revive the shock. When it collapses to a black hole, the neutrino emission essentially cuts off instantaneously. The neutrinosphere, the surface from which neutrinos last scatter before escaping, falls inside the forming event horizon. The neutrino signal simply stops. This sudden cessation of the neutrino signal is one of the most distinctive signatures of direct black hole formation. In a successful supernova, the neutrino emission continues for tens of seconds as the protoneutron star cools. In a failed supernova, the neutrino emission is brief. The duration from core bounce to black hole formation might be just seconds to minutes, and it ends abruptly. This is actually testable. For a supernova in or near our galaxy, close enough for neutrino detectors to detect the signal, the neutrino light curve would look very different for a successful versus a failed supernova. For the famous SN 1987A in the Large Magellanic Cloud, neutrino detectors on Earth registered about 20 neutrinos over about 12 seconds. For a failed supernova, the detectors would see neutrinos for a shorter duration, followed by an abrupt cutoff. This is the smoking gun signature of black hole formation that the neutrino astronomy community has been waiting for. Now let me tell you about what happens to the star's outer layers when the protoneutron star collapses to a black hole. When the black hole forms, it inherits the accretion that was feeding the protoneutron star. The infalling material continues to fall, but now, instead of landing on the surface of a neutron star, which has a hard surface at which energy is deposited, the material falls past the event horizon, contributing its mass energy to the black hole and radiating nothing in the process. The stalled shock, which had been hovering above the protoneutron star, now collapses inward as the infalling ram pressure overwhelms it. The shock that had briefly been the potential instrument of the star's explosion is swallowed by the forming black hole. What about the stellar envelope? The outer layers of the star, everything from the stalled shock region outward, had been sitting there, falling inward under gravity, while the shock drama played out in the core. When the black hole forms, these outer layers are still in free fall. The information that the black hole has formed travels outward at the sound speed in the stellar material, not at the speed of light. Because we're dealing with acoustic propagation through the stellar gas, not electromagnetic waves, the sound speed in the stellar interior is roughly 1,000 to 10,000 kilometers per second, much faster than the stellar freefall velocity, but much slower than light. For a red supergiant, a bloated, extended star whose outer layers might span hundreds of solar radii or hundreds of millions of kilometers, the acoustic wave carrying the information of the core's collapse might take days to reach the stellar surface. During this time, the outer layers continue their infall, unaware that the interior has formed a black hole. When the acoustic wave reaches the outer layers, or when the outer layers' free fall brings them within the growing black hole's gravitational influence, they begin to fall rapidly inward. The rate of infall depends on the black hole mass and the structure of the stellar envelope. For the most compact, most massive stars, this infall might be rapid. The outer layers fall into the black hole in hours. For extended red supergiants, the infall might take longer, the diffuse outer layers are weakly bound, and might take days to weeks to fall in. In some models, a brief optical transient is produced during this infall phase. The kinetic energy of the infalling material is partially radiated as the material approaches the event horizon. This transient is expected to be much dimmer and briefer than a supernova, perhaps a millionth of the typical supernova luminosity, perhaps lasting hours to days rather than weeks to months. This is the optical signature of a failed supernova. Faint, brief, easy to miss if you're not monitoring continuously with sufficient sensitivity, but in principle detectable. Now let me address the cases where even this faint transient appears to be absent, the apparently instantaneous disappearances. There are few ways to produce a disappearance that appears instantaneous in practice. The first is simply that the transient happened and was missed. If observations are separated by weeks or months, which is common in monitoring programs that aren't specifically designed for this purpose, a brief transient lasting hours to days would fall between observations and never be detected. The star would appear to vanish between two observations with no observed intermediate state for N6946 BH1. This concern is partially addressed by the monitoring cadence. The brightening that was observed in 2009, lasting several months, might be the failed supernova transient. The subsequent disappearance might be the final optical fading. The time scale is longer than the instantaneous description implies, but the 2009 brightening was modest compared to a typical supernova, consistent with a weak failed explosion. But for some of the other candidate disappearances in the literature, particularly the Kim dwarf LBV, the situation is less clear. The monitoring that was available doesn't constrain the timescale of the disappearance to better than roughly a year. Within that year, essentially any kind of transient could have occurred and been missed. The second explanation for apparently instantaneous disappearance is that some progenitor structures produce exceptionally faint and brief transients below the sensitivity thresholds of the monitoring programs. In very compact progenitors, the outer layers might be so tightly bound that they fall into the black hole very rapidly with very little energy radiated in the optical. The failed supernova transient for these events might be a few hours of emission at a luminosity far below current survey detection limits. The third explanation, and this is where the physics becomes genuinely exotic, involves the possibility that some stellar collapses are not the standard core collapse mechanism at all. Let me tell you about something that's been discussed in theoretical astrophysics for decades, but that's recently received renewed attention in the context of the disappearing star observations. It's called the quark star hypothesis. At the extreme densities reached in neutron star interiors, there's a theoretical possibility that nuclear matter undergoes a phase transition, that the individual protons and neutrons, which are each made of 3 quarks, dissolve into a sea of free quarks. The resulting object would be a quark star denser than a neutron star, supported by quark degeneracy pressure rather than neutron degeneracy pressure. Whether quark stars exist in nature is unknown. The theoretical prediction depends on the equation of state of dense matter at densities above nuclear saturation, which is currently unconstrained by laboratory experiments and can only be probed by observations of neutron stars and neutron star mergers. If quark stars exist, they have a maximum mass that might be different from neutron star maximum masses. And if a protoneutron star, while accreting matter during a failed supernova, undergoes a phase transition to a quark star, the dynamics of the collapse would change dramatically. Specifically, if the phase transition is rapid, if the conversion from nuclear to quark matter happens on a timescale shorter than the accretion timescale, it would release an additional burst of energy. This energy burst might revive the stalled shock, converting what would have been a failed supernova into a successful one with unusual properties, or it might produce a different kind of transient, a very brief, very energetic pulse of emission before the quark star itself collapses to a black hole. Some researchers have proposed that certain unusual transient events, not the standard disappearing star observations, but related phenomena, might be signatures of quark star formation during stellar collapse. The observational signatures are specific and potentially distinguishable from standard failed supernovae, though they require detection of neutrino and gravitational wave signals at high time resolution in addition to optical monitoring. This is speculative. The quark star scenario is one of several exotic possibilities that theorists have entertained when trying to explain phenomena that don't fit the standard picture. I include it not because it's established, but because it illustrates the range of physical possibilities that are currently on the theoretical table. Now let me tell you about something that's less exotic but potentially more relevant to the specific observed disappearances. The role of stellar rotation and magnetic fields in determining the outcome of stellar collapse. Rotation matters because a rotating core collapses differently from a non-rotating one. In a rapidly rotating core, the centrifugal force partially supports the infalling material, changes the geometry of the accretion flow, and dramatically alters the neutrino emission pattern. Rapidly rotating collapses produce asymmetric neutrino emission, strong magnetic fields in the protoneutron star, and potentially the formation of magnetically driven jets. These jets, magnetically launched along the rotation axis, are one of the proposed mechanisms for long gamma ray bursts, which we discussed in our conversation about the boat. In this picture, some massive stellar collapses produce both a failed supernova and a relativistic jet. The jet punches through the stellar envelope along the rotation axis, while the rest of the star falls into the black hole. For the observed disappearing stars, this might be relevant in the following way. If some of the apparently disappearing stars had high rotation rates, their collapses might have produced relativistic jets that were not aligned with our line of sight. We would see the star disappear, the optical photosphere collapsing into the black hole without seeing the jet because the jet is pointed away from us. This scenario, a directed jet accompanying an otherwise failed supernova, might explain some of the energy that appears to be missing from the simplest failed supernova models. The jet carries kinetic energy away along specific directions, while the rest of the star falls into the black hole almost silently. Stellar rotation rates in massive stars are known to vary considerably. Some massive stars rotate, rapidly rotating at speeds close to their breakup velocity, producing significant centrifugal distortion and internal mixing. Others rotate slowly, with minimal rotational influence on their structure. The rotation rate at the time of collapse depends on the star's entire angular momentum history, how much angular momentum it was born with, how much it lost through stellar winds over its lifetime, and how efficiently angular momentum was transported between different layers during the burning phases. For stars that lose significant mass through stellar winds, like luminous blue variables, the mass loss carries angular momentum away, reducing the core rotation rate. For stars that retain their envelopes, perhaps because they're in low metallicity environments where wind-driven mass loss is reduced, the core rotation might be higher. The Kinman dwarf galaxy has low metallicity. Low metallicity means reduced stellar wind mass loss. Reduced mass loss means potentially higher core rotation rates at collapse. This connection, low metallicity, high rotation, possible relativistic jet, might be relevant to why the Kinman dwarf LBV's disappearance was so clean and complete. Let me now address something that I think is important for putting all of this in proper scientific context. The question of how we distinguish between the various explanations, dust obscuration, failed supernova, exotic collapse, in specific observed cases. The key discriminant is the long-term infrared behavior. A star that has undergone extreme dust formation surrounding itself with an optically thick dust cocoon is still there. The stellar luminosity is still being generated just in the interior. The dust absorbs the optical light and re-emits it at longer wavelengths in the infrared. So a dusty obscured star should be visible in the mid-infrared at a luminosity comparable to its pre-disappearance optical luminosity. A star that has genuinely collapsed to a black hole is not there anymore. Its luminosity has ceased. There might be some residual emission from previously ejected material heated by the environment. But this should be much fainter than the original star's luminosity and should be declining over time. The infrared observations are therefore the critical test. Deep mid-infrared imaging of the disappearing star sites obtained with space telescopes like Spitzer and now Webb can distinguish between these scenarios. For N6946 BH1, the infrared observations show a faint source at the original star's position, much fainter than the original star that appears to be declining over time. This is more consistent with a genuine collapse than with dust obscuration, though the analysis is complicated by the contribution of a nearby star cluster to the infrared flux. For the Kinman dwarf LBV, the infrared situation is less clear. The host galaxy is at 75 million light-years farther than N6946. BH1's 22 million, making the infrared constraints weaker. Deep mid-infrared observations with Webb are needed to definitively constrain the presence or absence of the obscured star. This is one of Webb's most important contributions to the disappearing star investigation. Its infrared sensitivity and spatial resolution, far superior to Spitzer, can probe the infrared emission at the sites of stellar disappearances in nearby galaxies with unprecedented depth. If a star has genuinely collapsed to a black hole, Webb should see essentially nothing at the disappearance site. If it's dust obscured, Webb should see something, a bright mid-infrared source at the original stellar luminosity. The Webb observations of N6946, BH1, and similar candidates are being conducted and analyzed. The results, when fully published, will significantly clarify whether the leading candidates are genuinely disappearing stars or heavily obscured ones. Now, I want to tell you about something that connects the disappearing star phenomenon to one of the most important outstanding questions in stellar astrophysics, the compact object mass gap. We have good observational evidence for neutron stars, objects with masses typically between about 1.2 and 2.1 solar masses, the remnants of core collapse supernovae. We have good evidence for stellar mass black holes, objects with masses typically between about 5 and 100 solar masses, the remnants of the most massive stellar deaths. And we have evidence for gravitational wave events producing black holes and neutron stars across this mass range. But there's a gap, or at least an apparent gap, between roughly 2.1 and about 5 solar masses. In this mass range, we have very few confirmed compact objects. We have 1 or 2 candidates, astronomical objects, whose properties are consistent with being either very massive neutron stars or very low-mass black holes, but the mass range is strikingly underpopulated compared to the adjacent ranges. This gap, the mass gap, is either a real physical feature, stellar evolution, and collapse physics, somehow doesn't produce compact objects in this mass range, or it's an observational selection effect. Compact objects in this mass range exist, but are harder to detect than black holes or neutron stars in their respective ranges. Direct black hole formation from failed supernovae might address this gap. If the protoneutron star in a failed supernova accretes its way to the maximum neutron star mass and collapses to a black hole, the minimum black hole mass formed this way is roughly equal to the maximum neutron star mass, about 2 to 2.5 solar masses. And the maximum black hole mass formed this way might be limited by the amount of mass successfully accreted before the envelope disperses, potentially producing black holes of just a few solar masses. Failed supernovae might be preferentially producing black holes of 2 to 5 solar masses, exactly the mass gap region. If so, the apparent underpopulation of the gap is partly an observational effect. These black holes are formed without the supernova explosion that would leave a pulsar or a neutron star in an observable X-ray binary. The black holes sit quietly in the remnants of their former stellar envelopes with no companion star, no accretion, and no electromagnetic signature. This prediction that failed supernovae produce black holes specifically in the mass gap is testable with gravitational waves. As LIGO detects more compact binary mergers, the mass distribution of the merging objects will reveal whether there's a real physical gap or whether compact objects in the 2 to 5 solar mass range are simply not being efficiently detected through electromagnetic means. If LIGO detects a significant population of mergers involving compact objects in the mass gap, it would support the idea that failed supernovae are producing these objects regularly, just silently. Let me now address something that I've been building toward: the connection between disappearing stars, failed supernovae, and the broader question of how black holes form in the universe, specifically the formation of the most massive stellar black holes. Standard core collapse supernovae produce black holes through a specific channel. The protoneutron star accretes material from the fallback of supernova ejecta, material that was initially expelled by the explosion but that lacks sufficient velocity to escape the gravitational pull of the remnant. This fallback accretion can increase the black hole mass from the initial 1 to 2 solar masses to perhaps 5 to 15 solar masses in some scenarios. Failed supernovae potentially produce heavier black holes because instead of only the fallback accreting onto the remnant, essentially the entire stellar mass minus the neutrino and weak electromagnetic losses falls into the black hole. The resulting black hole might have a mass of 10 to 40 or more solar masses, depending on the initial stellar mass. This is a different channel for producing massive stellar black holes than the fallback accretion mechanism, and it might be more efficient producing heavier black holes in a single event rather than through the two-step process of explosion followed by fallback. The gravitational wave observations from LIGO and Virgo have now detected merging black holes with masses in the range of 7 to about 100 solar masses, with individual black holes occasionally reaching masses above 40 solar masses. These massive black holes are difficult to produce through standard supernova channels with realistic fallback accretion. Failed supernovae direct collapse of the most massive stars might be the primary formation channel for the most massive of the stellar mass black holes that LIGO is detecting. If this connection is correct, then the disappearing stars we're detecting optically, the N6946, BH1s, and the Kinman dwarf LBVs, are the precursors of the black holes that LIGO is eventually detecting in binary mergers. The optical disappearance and the gravitational wave detection are different epochs of the same story. A massive star collapses silently to a black hole. The black hole is born into a binary system or eventually forms a binary through dynamical interactions. The binary gradually decays through gravitational wave emission, and eventually the two black holes merge in a cataclysm that we detect as a gravitational wave event a billion light years away. I want to now tell you about something that sits at the intersection of the disappearing star phenomenon and fundamental physics. Something that has been discussed speculatively, but that I think deserves mention because it illustrates the full scope of what might, in principle, be happening. There's a class of theoretical objects called gravitational vacuum condensate stars, or gravar stars. And there's another class called black stars, or fuzzballs, in the string theory context. These are proposed alternatives to black holes, hypothetical objects that form when stellar collapse proceeds to extreme densities, but that don't form event horizons in the classical sense. They're supported against collapse by exotic forms of pressure, dark energy pressure in the gravistar case, string theoretic quantum pressure in the fuzzball case. I want to be completely clear that these are speculative theoretical proposals with no confirmed observational evidence. They're not accepted by the mainstream astrophysics community as likely descriptions of real objects. The evidence strongly favors classical black holes as the outcome of massive stellar collapse. But here's why I mention them in the context of disappearing stars. If these exotic alternatives to black holes existed, if stellar collapse sometimes produced a gravistar or a fuzzball rather than a classical black hole, the electromagnetic signature might be different from either a successful supernova or a standard failed supernova. The transition from a proto-neutron star to a gravistar might produce a specific energy release pattern. The endpoint object, rather than being completely dark, might have a faint electromagnetic glow from its surface, different from a neutron star, but also different from a black hole. These exotic alternatives are included in the theoretical discussions precisely because the observations of disappearing stars are ambiguous enough that they don't yet definitively confirm the classical black hole picture. The electromagnetic constraints on the final state, how much light, if any, is coming from the collapse site long after the initial disappearance, are one of the discriminants between classical black holes and exotic alternatives. The deep infrared imaging that Webb is conducting of disappeared star sites is, among other things, constraining these possibilities. A genuine classical black hole would produce essentially no detectable electromagnetic emission from the collapse site itself. Exotic alternatives might produce a faint, persistent emission. The current data doesn't show such persistent emission at the levels expected from the most optimistic exotic models, but the constraints are not yet tight enough to definitively rule out all possibilities. Let me close this. Second part with something that I think captures the state of the science beautifully. The intersection of the specific and the fundamental. The specific observation is this. A handful of massive stars in nearby galaxies have been observed to disappear without producing visible supernovae. Some of these disappearances are well explained by the failed supernova mechanism, the theoretical prediction of direct black hole formation that stellar physicists have been refining for decades. Others remain ambiguous, with competing explanations that haven't yet been distinguished by the available data. The fundamental implication is this. We are, for the first time, beginning to directly observe the formation of black holes in real time. Not the merger of existing black holes, which LIGO detects in gravitational waves, but the actual birth of black holes from the collapse of massive stars. The moment when a star that had been burning for millions of years simply ceases to exist as a luminous object and becomes an invisible gravitational concentration. This is one of the most fundamental physical processes in the universe. Black holes are not exotic or unusual. They're the natural endpoints of the most massive stellar lives, and they're extraordinarily consequential for the structure and evolution of galaxies, the synthesis of heavy elements, and ultimately the conditions for life. Watching them form directly in real time by observing the stars that collapse to produce them is an extraordinary capability that we are only now developing. The instruments are improving. The monitoring programs are expanding. LSST will watch millions of stars. Webb will characterize the infrared aftermath of disappearances with unprecedented sensitivity. The Einstein telescope will listen for the gravitational wave signature of stellar collapse at cosmological distances in part 3. I want to bring all of this together into the bigger picture of what vanishing stars tell us about stellar death, about black hole demographics, and about the fundamental connection between the deaths of stars and the origins of everything we can see. Because a star that vanishes instantly is not just a mystery, it's a window into what happens when gravity finally wins. So we'd arrived at this place where the disappearance of massive stars, confirmed by observation, motivated by theory, and still partially unexplained in its details, is teaching us something fundamental about the endpoints of stellar evolution and the formation of black holes. The failed supernova mechanism provides the physical framework. The specific observations test and refine that framework. And the next generation of instruments will determine how common stellar disappearances are, what their demographic distribution tells us about stellar physics, and whether some of the more exotic possibilities have any observational reality. Now I want to bring it all together to ask what the vanishing of stars tells us about the universe we live in, about black holes not as abstract mathematical objects, but as real physical entities that form, that grow, that influence everything around them, about the connection between stellar death and the conditions for life, and about what it means to live in a universe where some of the most massive objects silently disappear rather than announcing their ends. Let me start with something that I think is underappreciated: the demographics of stellar death. The universe contains an estimated 2 trillion galaxies. Each galaxy contains somewhere between 100 billion and 1 trillion stars. The Milky Way alone, with its roughly 200 billion stars, is currently forming stars at a rate of about 1 to 2 solar masses per year, producing perhaps a few new massive stars per century. Over the history of the Milky Way, about 10 billion years, this star formation rate has varied, but the cumulative production of massive stars is enormous. Roughly 1 supernova per century in the Milky Way. The standard estimate implies that over 10 billion years, our galaxy has experienced something like 100 million supernovae, each one leaving behind a neutron star or a black hole. If the failed supernova fraction is 10 to 30% of massive stellar deaths, the current theoretical expectation, then the Milky Way contains somewhere between 10 and 30 million stellar mass black holes formed through direct collapse, in addition to the neutron stars and black holes produced by successful supernovae. This is a staggering number. 10 to 30 million black holes, each with a mass of perhaps 5 to 40 solar masses, scattered through the disk and halo of our galaxy. The vast majority of them isolated, no companion star, no accretion, no electromagnetic emission, completely invisible except for their gravitational influence on nearby matter. We've detected perhaps 24 stellar mass black holes through X-ray binary observation systems, where the black hole is accreting material from a companion star and emitting X-rays in the process. And LIGO has detected perhaps 100 through gravitational wave observations of binary mergers. These numbers are tiny compared to the expected total population. The universe is full of invisible black holes. Failed supernovae are producing them continuously, silently, every time a massive star crosses the threshold between exploding and collapsing. It adds one more to the census of dark objects scattered through the galaxy. Now, let me tell you about what this implies for the chemical evolution of the universe, for the production and distribution of the heavy elements that everything, including us, is made of. Successful supernovae are the primary mechanism by which heavy elements produced in stellar cores are distributed into the interstellar medium. The explosion, the shock wave that blows the star apart, drives the material outward. The heavy elements mix with the surrounding gas. Future generations of stars form from this enriched material. The process repeats, each generation more chemically enriched than the last, gradually building up the heavy element abundance that allows rocky planets and complex chemistry and biology. Failed supernovae disrupt this picture in a specific way. A massive star that collapses directly to a black hole without a visible explosion doesn't distribute its heavy elements. The silicon, oxygen, carbon, iron, and all the other elements laboriously synthesized in the star's core and outer layers fall into the black hole. They disappear behind the event horizon. They're lost to the interstellar medium. This has a cumulative effect on chemical evolution. If 10 to 30% of massive stellar deaths are failed, if that fraction of the heavy elements synthesized in massive stars are swallowed rather than distributed, then the rate of chemical enrichment is slower than calculations based solely on successful supernovae would suggest. The magnitude of this effect depends on which stars fail and which succeed. If the failing stars are predominantly the most massive ones, stars above, say, 40 solar masses, then the elements specifically produced in these very massive stars would be preferentially lost. These include specific products of massive star, nucleosynthesis, oxygen, silicon, sulfur, and heavier elements produced in the silicon-burning shell that would be swallowed rather than expelled. The specific pattern of chemical abundances we observe in the interstellar medium and in old stars, the ratio of different elements to each other, encodes information about the history of stellar death. If failed supernovae are common and preferentially involve specific stellar mass ranges, that information is encoded in the chemical abundances. Detailed spectroscopic surveys of chemical abundances in stars of different ages, the archaeochemistry of the galaxy, might in principle be used to constrain the failed supernova fraction. This connection between vanishing stars and the chemical history of the universe means that understanding stellar disappearances is not just an esoteric astrophysical question. It's a question about why the universe has the chemical composition it does. And since the chemical composition of the universe determines what kinds of planets can form and what kinds of chemistry can operate, it's ultimately a question about the conditions for life. Let me now take you to something that I find genuinely beautiful about the disappearing star story. The way it connects to gravitational wave astronomy in a specific testable way. LIGO has now detected roughly 100 gravitational wave events from merging compact objects, mostly black hole binary mergers, with a handful of neutron star mergers and mixed events. The masses of the merging black holes span a range from about 5 to about 100 solar masses, with a distribution that encodes the history of black hole formation. The mass distribution is not uniform. There are features, a peak at certain masses, a possible dip at certain mass ranges that reflect the astrophysics of black hole formation. Decoding these features requires understanding the multiple channels through which black holes form and pair up into binaries. One of the key inputs to this decoding is the mass function of newly formed black holes. The distribution of mass is produced by different formation channels. Failed supernovae produce black holes with masses related to the progenitor stellar mass, modified by the amount of mass lost in winds before collapse and the amount accreted after collapse. Successful supernovae, followed by fallback, produce lighter black holes. The optical monitoring surveys watching for stellar disappearances provide direct constraints on the mass function of newly formed black holes from failed supernovae. If we can identify the progenitor mass of each disappearing star and the mass of the resulting black hole, we can build the formation mass function empirically. This is happening. The progenitor stars of the candidate failed supernovae are being characterized from archival Hubble images measuring their luminosities, colors, and derived masses before they disappeared. The resulting black hole masses are being constrained from the infrared afterglow properties and from the gravitational wave rates. Over the next decade, as LSST discovers dozens to hundreds of failed supernova candidates and LIGO successors detect thousands of gravitational wave events, the connection between the optical disappearances and the gravitational wave population will become much tighter. We'll be able to directly trace the black holes that LIGO detects back to the stellar deaths that created them, a complete accounting of black hole birth from stellar disappearance to compact object merger. Now, let me address something that connects the disappearing star phenomenon to cosmology, to the large-scale structure of the universe, and to one of the outstanding puzzles in observational astronomy, the missing baryon problem. Most of the ordinary matter in the universe, the baryons, the protons and neutrons that make up atoms, is not where we can see it. The cosmic census says there should be about 4 or 5% of the universe's total energy density in baryons. But when we add up all the matter we can see in galaxies, in hot gas, in galaxy clusters, in the warm, hot intergalactic medium, we account for only part of this. The rest, perhaps a third to half, of all baryons appears to be missing. This missing baryon problem is distinct from the dark matter problem. We're not looking for exotic, non-interacting particles. We're looking for ordinary hydrogen and helium that's hard to detect because it's in a specific temperature range or density range or location that our surveys don't efficiently capture. One contribution to the missing baryons that's sometimes overlooked is the mass swallowed by black holes during failed supernovae. Every failed supernova converts stellar mass into black hole mass, taking baryons that were in the form of atoms in a stellar envelope and converting them into mass energy behind an event horizon, inaccessible to future observation. This is not a large effect. The total mass in stellar mass black holes is much smaller than the total baryonic mass in galaxies, but it's one more contribution to the inventory that needs to be accounted for. More importantly, the stellar winds blown off massive stars before their collapse, the mass lost in the decades to millennia before the stellar death, enriched the circumgalactic medium and the intergalactic medium with warm, diffuse gas that's hard to detect. Failed supernovae, by not producing the energetic explosions that would drive this material outward into the galaxy halo and beyond, might result in a different distribution of this mass compared to successful supernovae. The circumgalactic medium around galaxies with high rates of failed supernovae might be different, less enriched in heavy elements at large radii from the circumgalactic medium around galaxies with predominantly successful supernova deaths. These are subtle effects that require detailed modeling and careful observations to characterize, but they illustrate how the apparently local astrophysical question of stellar death connects to cosmological questions about the large-scale distribution of matter. Let me now tell you about something that I think is the most profound implication of the disappearing star phenomenon, something that connects it to the fundamental question of how the universe generates the conditions for complexity. Stars are the universe's alchemists. They take the hydrogen and helium produced by the Big Bang and transmute them into the heavier elements: carbon, oxygen, nitrogen, silicon, iron, and all the rest that are necessary for solid planets, liquid water, organic chemistry, and ultimately biology. This alchemy operates through nuclear fusion in stellar interiors, and it requires two things: the production of heavy elements in the first place and their distribution into the interstellar medium, where they can be incorporated into new generations of stars and planetary systems. Both parts of this process depend on stellar death, and both are affected by the failed supernova fraction. If a quarter of all massive stellar deaths are failed, if a quarter of the universe's most powerful alchemists swallow their products rather than distributing them, then the chemical evolution of the universe is fundamentally altered. The universe we actually live in has been chemically enriched by the combined action of all the stars that have died throughout cosmic history. The specific chemical inventory of our solar nebula, the mix of elements from which Earth and all life on it is built, reflects the integrated output of billions of years of stellar nucleosynthesis and distribution. If the failed supernova fraction were zero, if every massive star exploded and distributed its products, the universe would be more chemically enriched sooner. Rocky planets might have formed earlier. Life might have had more time to evolve on more worlds. If the failed supernova fraction were much higher, if most massive stars collapsed silently rather than exploding, the universe would be less chemically enriched. Rocky planets would be rarer. Life, if it arose at all, would have fewer of the heavy elements that biology exploits. The observed failed supernova fraction, whatever it turns out to be, is one of the parameters that determines the chemical character of the universe. It's not arbitrary. It's determined by stellar physics, by the structure of stellar cores, by the efficiency of neutrino-driven shock revival, by the equation of state of dense nuclear matter. But it has cosmological consequences that ripple forward through billions of years of galactic chemical evolution. In this sense, the stars that vanish silently are not just interesting astrophysical anomalies. They're part of the fundamental machinery of the universe, participants in the process that determines whether worlds like Earth can exist and whether life like ours can arise. Let me now come to something that I think is philosophically important about the entire disappearing star story. Something about what it means to live in a universe where some of the most powerful processes are silent. We are creatures of light. Our primary sense is vision. We evolved on a planet where sunlight illuminates the world and enables the detection of objects, threats, food, and conspecifics at a distance. Our astronomy is fundamentally an astronomy of light. We've extended our visual sense with telescopes that capture photons from across the electromagnetic spectrum, but photons are still what most of our instruments detect. In this light-centric universe, we've naturally assumed that the most powerful events are the most luminous ones, supernovae. Gamma-ray bursts, quasars. These are the events that announce themselves across cosmic distances in photons. They're the loudest voices in the electromagnetic universe. But failed supernovae are telling us something different. The most massive stars, the ones with the most nuclear fuel, the most gravitational potential energy, the most mass to convert into energy, are sometimes dying silently, not with a shout, but with a disappearance. The most energetic available gravitational collapse, a star of 40 solar masses falling into a black hole, is occurring without any significant electromagnetic emission. The photons that we see are not the story. The story is in the gravity. This shift from an electromagnetic picture of the universe to a gravitational one is the deeper revolution that gravitational wave astronomy is bringing. LIGO is showing us that the universe is doing extraordinary things without light. Merging black holes, which produce no electromagnetic emission, are producing space-time distortions that carry more power than anything visible in the universe. Failed supernovae are adding to this picture. The most massive stellar deaths are happening in darkness. We are just now developing the sensory apparatus to detect this dark universe. Gravitational wave detectors are our first instruments for the non-electromagnetic cosmos. They're revealing events and phenomena that were always happening but that we were completely blind to because our entire observational history had been built on light. The stars that vanish are one manifestation of this dark universe. Their disappearance is our first optical glimpse of events that are fundamentally gravitational events that the universe is performing for an audience of gravitational wave detectors that we're only now building. Now let me bring this all the way back to the beginning, to the sentence that started this conversation. It vanished instantly. I've spent 3 parts tracing what we know, what we don't know, and what we're working to find out about stars that disappear. The failed supernova mechanism provides the physical framework. It's the best current explanation for most of the observed disappearances. The specific observations are ambiguous enough to leave room for other possibilities. The next generation of instruments will substantially clarify the picture. But here's what I want to say about that original sentence, about the phenomenology of the vanishing, before all the physics, because I think it captures something genuinely important. When a star vanishes, when something that was there, that had been there for millions of years, that has been producing 10,000 times the sun's luminosity for the entire history of civilization, simply stops being there. It's not just an astronomical event. It's a statement about the nature of physical reality. Physical objects don't usually vanish. Things persist. Matter and energy are conserved. The first law of thermodynamics doesn't allow energy to simply disappear. A star that ceases to exist as a luminous object hasn't violated any conservation law. Its mass energy is still there behind an event horizon, contributing to the gravitational field of the black hole that formed. But from the perspective of an outside observer, from our perspective, the electromagnetic manifestation of that mass energy is gone forever. No light will ever reach us from the matter that's now inside the black hole. In a specific physical sense, something has been removed from the observable universe. Not destroyed. Physics doesn't allow destruction, but rendered permanently inaccessible. The star's matter is still there in some sense. But we can never interact with it, never receive information from it, never probe it in any way. It has crossed a one-way boundary. The event horizon is the most radical boundary in nature, more radical than the edge of the observable universe. Light from beyond the Hubble volume can in principle reach us as the universe evolves. The event horizon is a boundary from which nothing can ever escape, not even in principle, not even in the infinite future. It's the universe's most permanent wall. And when a massive star collapses directly to a black hole, when it vanishes without the explosion that would scatter its material into the galaxy, it takes that wall with it. The star's carbon and oxygen and iron and silicon elements that might eventually have become part of a planetary system, part of rocky terrain, part of chemistry, part of life, fall silently behind the event horizon, permanently inaccessible. There's one final thing I want to say about disappearing stars, and it connects to a theme that runs through many of our conversations about extreme astrophysical phenomena. The theme of what these phenomena reveal about the fabric of physical law: black holes are the universe's most extreme test of general relativity. Regions of space-time where the curvature is so extreme that it severs the causal connection between inside and outside, where the future of any infalling object is bounded by the singularity, not by any possible escape. General relativity, pushed to its absolute limit, predicts the existence of these objects, and the observations of stellar mass black holes in X-ray binaries, of supermassive black holes at galactic centers, of merging black holes in gravitational wave observations confirm that black holes are real physical objects, not mathematical.
As the tension between theory and experiment deepened, the scientific community found itself standing at a crossroads. The confidence that had defined 19th century physics began to erode, replaced by a growing awareness that something fundamental was missing. The anomalies were no longer isolated curiosities. They were signals pointing toward a deeper inconsistency in the way nature was understood. Yet the path forward was unclear, and the tools that had once seemed so powerful now appeared limited when confronted with these new challenges. One of the reasons this crisis was so difficult to resolve was the sheer success of classical physics in other domains. The motion of planets, the mechanics of engineering systems, and the propagation of electromagnetic waves all continued to be described with remarkable accuracy. There was no obvious reason to abandon a framework that worked so well in so many contexts. This created a paradox. The theory was both extraordinarily successful and fundamentally incomplete at the same time. Physicists began to recognize that the problem might lie not in the equations themselves, but in the assumptions that underpinned them. The idea that energy could vary continuously, for instance, had never been directly tested at very small scales. It was an assumption that made sense within the macroscopic world of everyday experience, but there was no guarantee that it would hold true in all situations. Similarly, the concept of determinism, the belief that the future could be predicted exactly from the present, was being called into question by phenomena that seemed inherently unpredictable. At the heart of this growing uncertainty was the realization that the microscopic world might operate according to different rules than the macroscopic one. Classical physics had been developed primarily to describe large-scale systems, where the effects of individual particles could be averaged out. But as experimental techniques improved, scientists were able to probe smaller and smaller scales, revealing behaviors that did not fit neatly into the classical picture. The study of radiation played a particularly important